Hey folks, it's our last lecture on thermodynamics, woohoo! So this one is all about heat engines in particular. So our goals for this lecture are first of all talk about what a heat engine is and what it does and how it works basically. Then we'll do some analysis of heat engines and the work and heat involved in their functioning by solving problems involving heat input and heat output as well as work done. And then lastly, we'll use those three different numbers to also calculate the efficiency of a heat engine to evaluate how effectively it works. So we'll go ahead and get started. So first of all, a basic definition for a heat engine is any sort of device that can convert thermal energy, basically the energy of like heat and molecular motion, and convert it into mechanical energy, an energy that we can actually use to do work on other objects. Now basically, a simple way to think about the functioning of a heat engine is this. First of all, the heat engine takes in heat energy. It then uses some of that energy and turns it into work. It uses that energy to power it doing work on its surroundings. And then whatever heat we took in but didn't convert into work is then expelled from the engine. So let's take a look at that a little bit more closely by looking at this animation right here. So what we see is a standard 4-stroke heat engine, very similar to the one that might power your car. We've got 4 different steps involved in this, so what I'm going to do is slow this down and talk you through each one. Yeah, there we go. Okay. So our first step that we're going to talk about is this one right here. See, this is called the intake stroke. What just happened is by the mechanism here, as it comes down, it pulls the piston downward. That pulls in a mixture of air and fuel. So basically, this valve right here leads off to your gas tank. And so by pulling down on the piston, we see that gas and fuel, gas and air get pulled in to our cylinder. So that's our first step. Okay, then what just happened there is as the gear continued to move around, it pushed back up on the piston. That compressed the gas, compressed it really small, increased the temperature of it as well. Right at the top of this compression is when the spark plug fires, and that ignites all of this compressed gas mixture of fuel and air, which we'll see right there. Wha-bam! All right, so it heated up very quickly, and all of that energy from that ignition, that rapid rise in temperature, drove the piston downward. Okay, this is where we really get the power behind our engine functioning, is that rapid expansion of the hot combusted air, basically. And then finally what we'll see is we'll open this valve and we'll be able to push all of that combusted air back out. There we go. Alright, so once again we'll go through it step by step. We have the intake, gets compressed. Here's where we get all that heat energy that drives this gear around, and that's what enables our car to drive, basically. It's what then is able to be converted into usable work that can power other mechanisms. Okay, so that's just a very basic introduction to how engines work. If you want to take a look at this more closely or look at some other examples of engines, feel free to go to this website, animatedengines.com. It's got all sorts of different types of engines in there, and it's laid out really nicely, so I highly recommend it. Now, back to this old guy. All right, you've already seen that. Okay. Now obviously it would be difficult for us to, draw an animation every time we wanted to represent what was going on in an engine. So I've got a pretty generic model here for you about all the different things that are happening in a heat engine. So right here in the center we've got our heat engine. And the main input to that is heat energy from some sort of high temperature source. Now in the engine I just showed you, that was the heat from the ignition and the combustion of that gas and air mixture. So that was our high temperature source that gave us all this energy. Right? Then what the heat engine does is it's able to use some of that energy to do work. In the case of the engine we just looked at, the work that was being done was the expansion of the gas driving the piston downward. Okay. But we are going to have some heat that doesn't get converted into usable work, that just remains heat. That ends up getting expelled into some sort of low temperature reservoir. So if you see your exhaust coming out of your car, especially early in the morning when it's easy to see the hot exhaust coming out, that would just be the waste heat that is being dumped out of the heat engine after it's already used what it could from this high temperature source. Now, if we want to calculate the amount of work we can get out of our engine, it's very simple. We know that ultimately all the energy that's coming in is going to have to go out again, either as work or as this heat waste. All right. So based on that idea, we know that the amount of work done is just the difference between the amount of heat that came in and the amount of heat that came out. So work is heat transferred in, which is represented by QH, the heat from the high temperature source, minus QL, the heat given to the low temperature source afterwards. Okay. All these are measured in joules, and we're going to keep all of those values positive. Okay. So don't worry about whether it's coming in or going out, negative or positive like we did last time. Here, we're just going to keep all of our values positive. So let's try that out. Sample problem. We have some specs on a heat engine, the energy that it takes in as heat from its high temperature source, as well as the work that it does. We're trying to figure out then how much heat goes into that low temperature reservoir, how much heat did we basically waste during this process. So some things we know. We know the heat input is 4,500 joules, so we'll set that equal to QH, because QH tells us our input heat. We know the work done was 2,750 joules. We're trying to find the heat waste, or QL. Now work is equal to the heat input minus the heat output. If we want to rearrange that to solve for just the heat output, we will do that as such. And then we can just plug everything in. So we've got 4,500 minus 2,750. That leaves 1,750 joules of heat energy that didn't get used and now have to be just expelled as exhaust. Right. Now, in an ideal world, we would be able to convert all of our heat energy that comes in into usable work, because that really is the goal of the heat engine, is to create work out of this heat source. Unfortunately, though, it doesn't really work that way in the real world. There's pretty much always going to be some heat that doesn't get converted into work, the same way that it's really impossible to create a frictionless surface. There's always going to be some friction involved whenever you have any two surfaces sliding across each other. Just one of those things, right? But again, we're trying to maximize the amount of work that we can get out of a heat engine. So basically, the more work we can get, or the less heat that we waste, the more efficient we say that engine is. So we can evaluate the effectiveness of an engine based on how much of the heat energy that it takes in can be converted into work. So we can then calculate a number to go with that efficiency using this equation, or actually these two equations. We've got two different ways to calculate the efficiency of a heat engine depending on what values we have available, what values are known to us. Okay. EFF stands for efficiency. It's just a number. There are no units associated with it. It can't be any less than 0 because you can't get negative work out of something. And it can't be any greater than 1, otherwise we've created energy out of nothing, which would be cool, but not going to happen anytime soon, right? So one way that we can calculate the efficiency of a heat engine is to take the work output and divide that by the heat input, okay? So this is one way that we can calculate the efficiency of our heat engine. Sometimes, though, we won't have the work, but we will know the heat output. If that's the case, then we can also just use this equation. It's totally the exact same thing, just rearranged. Okay? We can also use the equation 1 minus, and then we just take our heat output divided by our heat input. Okay? Again, as before with calculating the work from a heat engine, just make all the values positive. Don't worry about positives and negatives here. Okay. So one more sample problem for you guys. We've got a steam engine. It takes in 64,500 joules of heat input from the boiler. It then spits out 53,900 joules of exhaust or heat waste during one cycle. We're trying to figure out how efficient is that engine, how good is it at turning heat energy into work. So we know the heat input QH and we know the heat output QL. We don't know the efficiency. Right? Now we have our two options in terms of which equation we want to use. I'm going to choose this one because that way I don't have to calculate work. I can just already plug in all the values that I know. So that means the efficiency is equal to 1 minus, and then the fraction QL divided by QH. And as we just plug that in, we get an efficiency of 0.164 or 16.4%. Either way is totally fine to write it. Just a little note, this 1 right here is not part of this fraction. So do this division first and then subtract whatever you get from this calculation from 1 to get your final efficiency. We've got some sample problems as well as their solutions on SharePoint, so be sure to check it out, and I will see you guys soon. Take care. Bye.